Good morning to all. Myself P. Janagaratnam from Department of Mechanical Engineering, SNS College of Technology. In my previous session, I already discussed about the finite element formulation and heat transfer, basic heat transfer. Today, I am going to solve one heat transfer problem. The problem, a wall has 0.6 meter thickness having thermal conductivity of 1.2 watt per meter Kelvin. The wall is to be insulated with a material of thickness 0.6 having an average thermal conductivity of, and the inner temperature is 1000 degrees Celsius, and outside the insulation is expressed to the atmospheric air at 30 degrees Celsius with heat transfer coefficient of 35 Weber per meter squared Kelvin. Calculate the nodal temperature. So wall, and we are having, first we have to write down the given data: thickness of the wall given, thermal conductivity given, thickness of the insulation may be given, and the other temperatures. So now we are having two elements, one is the wall and another one is insulation. So the element 1 means node 1 and 2, and element 2 means node 2 and 3. So we are having totally three nodal temperatures, T1, T2, T3, and thermal conductivity K1, K2, and length of the element 1 and 2, L1 and L2. So we are having the conduction with the convection. There is no internal heat transfer, heat generation. So we have to calculate the nodal temperature. First we have to calculate the finite element equation for the element 1. Normal finite element equation is equal to F is equal to K into T. So F, K and T, and we cannot give the area value, so we can assume that the area is equal to 1 meter squared. After that we have to calculate the finite element equation for the element 2. After that, in our first element we are having only conduction, and second element we are having both conduction and convection. The finite element equations will be varied. This and all I already discussed in my previous videos. So we can combine these two finite element equations, we will get the assembled finite element equation. So here we are applying the forces and other values. After that we have to follow certain steps to find out the nodal temperatures. The first step is the first row and first column of the stiffness matrix K have been set equal to 0. Expect the main diagonal values. So we can convert the first row and first column, which will be converted into 0, except main diagonal value, which will be converted into unit matrix 1. So this can be written as this. So the second one is the first row of the force matrix is set or replaced by the known temperature at node 2. So here the first force matrix, which will be replaced the known temperature. Already we are knowing the known temperature value is equal to 1273 Kelvin. So we can replace the first force matrix value, which will be equal to the known temperature at node 2, which will be equal to 1273. The third step, the second row first column of the stiffness matrix K value is multiplied by the known temperature at node 1, which will be the first second row and first column means -2. This is -2 multiplied by the known temperatures, we will get -2546. Again this value will be replaced by the second force matrix. So 2546, which will be replaced in that second force matrix. After that we are solving the above equations. We will get 7 into T2, we will get 7 T2, and minus 5 into T3 minus 5 T3 is equal to 256. This is equation number 1. And minus 5 T2 plus 40 T3 is equal to 10.605 into 10 to the power 3. This is the second equations. By using calculator we can directly solve these two equations. We will get the T2 or T3 values. Again, or we can directly solve this equation is multiplied by 5 and this equation is multiplied by 7. We can easily neglecting the T2 values, only the T3 value is available. So we can easily solve these equations. We will get the T3 value as 341.03 Kelvin. After that we can substitute this T3 value in any equations, we will get the T2 value. So T2 value which will be equal to 607.313 Kelvin. So our nodal temperature is gradually decreased. The initial temperature value is 1273 Kelvin. After that convection is converted into convection, free end convection, it will be gradually reduced. So second nodal temperature is equal to 607 and third nodal temperatures will be equal to 341. So this is the way we have to solve the heat transfer problem. Thank you.